Okay, so okay, hi. So today's consultation. So I think I received a question already asking about because Prof in one of the exercise sheets, sorry, the lecture notes, he mentioned that you don't need to show, you don't need to come up with the reductions yourself, but rather you need to only prove that it's correct. So let's open that part of the notes. Okay, so he mentioned here that he will not expect that we can come up with an involved reduction, but will be responsible for proving the validity. And so whether like we went through the proving of validity before. So in a sense, like I think when you prove your tutorial questions, sorry, your assignment questions, when you come up with the reduction, showing that the yes instance from the yes instance corresponds to yes instance of the other problem, that's the way you prove it actually. So that's the kind of proof that we are, I believe, like prof is expecting. So maybe let's say, for example, right? So in week 11, we went through several questions. I can imagine if maybe, right, if I understand prof correctly, what happens is that the questions could be something like, let me see. It was one of the questions. So, okay, the question would be maybe something like, you're given this problem, partition, and you're given another problem, ball partition. So what might be given in the exam is that they will describe that, okay, now we have a problem in partition, we have the input to it. So they perform a reduction by summing up the elements and then use this value as the result for ball partition. So to disprove, then you just have to give a counter example where on one side is a yes instance, but it becomes a no instance on the other side. So that's one. Okay. So like this over here is a counter example, right? You can revisit the slide slowly, but just saying that it's possible that reduction is wrong because you can give a counter example. But on the other hand, there can be reduction which is correct. So for example, in the exam, maybe prof will give you two problems, right? The partition problem and the knapsack problem. And then he will propose that, okay, here is the reduction. The reduction is by summing up everything, and then the W and the V is S over 2, S over 2. So I understand maybe you don't remember the full details, but like I can imagine maybe prof giving this kind of like reduction, and then you have to prove that it's correct by showing the yes instance to a partition implies a yes instance to knapsack. And then you do this argument like how come it's a yes instance, how come the yes instances is implied. And then you prove also the other way around. The other way around is proving that yes to knapsack is implying a yes to partition. So that is, I believe, what might be expected of you in an exam. But again, like this is just based on what I observed from this lecture notes that prof released. Does that clarify? No problem. Yeah. Yep. Okay. So a lot of people joined in while I was talking. So just now it was just a question about what is it actually, what does prof actually mean for us to be responsible for proving the validity? It just simply means that you are able to answer this question. So yes instance of one implies the other, then and vice versa. And also, of course, that it runs in polynomial time, but usually running in polynomial time, the proof isn't as difficult, I would say. Yeah, so that was a question we had just now. Yep. I'll just be doing my own work. Anytime like you have question, just speak up or put in the chat. If I don't notice the chat, just speak up. I'll pause the recording so that it won't be too long. Okay, so are you there? Like I'll resume with the question. So the question is about I just put in the chat first, week 6 assignment 2. going through week 6 assignment. Week 6 assignment question 2. Okay, so this is the question. Let's go through the question one by one. So it says here that you are given a stream of updates about items drawn from universe 1 to n. So you have items drawn, the items that you receive, right? The number is from 1 to n. Okay, so an example is given later on saying that, for example, 1 to 7, right? Then they introduce this notion of streams frequency factor. Okay, and what is this frequency factor? So f is an element of Rn. It just means that it's a vector of n elements. Okay, so then it says that the ith component, fi, they define as fi, is the frequency of item I in the stream. Okay, so let's go through this particular example. So here, right, the example they give is that the universe is size 7. So they are n equals to 7, right? So notice here how the adding, you add 5 and add 5. That means for 5, for f5, this will be like 1 plus 1, which equals to 2. And that's what you observe over here, in the 2 over here. Whereas for 7, this is equals to 1 plus 1 minus 1. This is the 3 things you see over here. So in the stream, like at the end of the day, when you are saying that I want to add 7, delete 7, the frequency vector kind of like tells you the frequency at the end of the day. At the end of the day, what's the frequency that I expect, right? At the end of the day, how many elements do I expect in the stream? Because I've added some elements and I've also deleted some elements. Okay, so the context clear so far, the meaning of frequency factor? Okay, great. So now, the next thing they introduce is this thing called a linear sketch. So a streaming algorithm is said to maintain a linear sketch of size k if it stores in memory AF for a matrix A that is fixed at initialization. Now, let's unpack this, okay? So first of all, notice how it maintains a linear sketch. It's a property of the algorithm, right? So it's like saying, it's like describing an algorithm. We say that it maintains a linear sketch. Okay, maybe an analogy could be something like, we say that an algorithm is polynomial time, right? That kind of thing. So this linear sketch is a property of the algorithm. Then what does it mean? Like I was initially confused when it says if it stores in memory AF. What does it actually mean? So it just means that you use a storage, that is of size k. Why? Because let's say I have a matrix A. Okay, let's make it longer. This is matrix A. The matrix A, they say it's k by n. Okay, so this is k, this is n. Then you multiply by f. You multiply by f. Okay, oh, there's space, great. So this is n. Okay, and remember f is Rn. F is in Rn, so it's a vector of size n. You matrix multiply these two things. Okay, so you can imagine that this is actually a 1 by sorry. I think I drew it wrongly. So I think it should be something like this. Give me a second, yeah. K by n. Oh no, I think it was correct. So this is n, this is 1. This is f. Sorry for the confusion. So f is still like a matrix of n by 1, can imagine. Okay, then you do a matrix multiplication and you get back a value that is of length n. Because why? This is a k by n matrix times a n by 1 matrix. Then you get something of length 1. Okay, so maybe I'll extend this a little bit just so that it's a bit clearer. This is A, this is K, this is N. So you get something that is like K by 1. Okay, so you get something like something like this. This is K, this is 1. Okay, so Yep, sorry about that. Yep, just now it was good. So okay, so we say that it's a linear sketch. A streaming algorithm is a linear sketch if you maintain this particular like array, like maybe an array of k by 1. Okay, so you want to maintain a k by 1 array, and if you maintain this where this can be obtained by having like the frequency vector times the sum matrix A, then we say that the algorithm is a linear sketch. Okay, so I hope like why it's called a linear sketch for now is clear. Okay, so now the first question says that we discussed an algorithm in class for frequency estimation, and we want to show it's a linear sketch. And then to show that something is a linear sketch, we have to explicitly say what the matrix A is, right? And then we want to use that matrix A to say that matrix A multiplied by our frequency at the end of the day actually gives us what the exact thing that we are trying to maintain in the algorithm. So this part is slightly confusing maybe, okay, but maybe hopefully if we go through an example, it becomes clearer. So this is the algorithm that we see in class, okay? The streaming algorithm is very simple. It says, I choose a hash function that maps the universe. So remember the universe is, you have n elements, right? So this is from Rn. We take it from the Rn, and then we map it to k elements, right? Map it to k elements. Then what we do is, okay, so let me call it table T, because in answer key they use table T. We maintain a table. The table has k elements, okay? Yes, k elements, or maybe let's use the convention that we used earlier. This is k by 1. Sorry, the k length is a bit inconsistent, but just want to deliver the idea. Then it says that what happens is that in the algorithm, when you get an element j, and recall that j is from Rn also, you use the hash function. You use the hash function, map it down to one of the k elements. Okay, map it down to one of the k elements, and then you increment the entry. Okay, so for example, if the number 5, right, this is from Rn, maybe it maps to slot 1, for example. So this particular slot here will be it'll be +1 here. Okay, then if you see 7 and it maps to like slot number 3, then this one here you +1. Okay, so this 0, 1, 2, 3. For example, like let's say k equals to 4. Okay, so and if we see a delete, then we do the opposite. We do a -1. Okay, so this is the algorithm. Then at the end of the stream, to estimate the frequency vector, they say that they'll estimate the frequency fi by returning AHI, by returning like a value from over here. We consult the value in the table. Okay, so that's the argument. So now what do we want to do is to show that why is this a linear sketch? Okay, and I think I haven't spent too long on this question. So I haven't spent too long on this question, so I can't exactly like comment on how you might arrive at the answer, but maybe I can at least go through the answer. Okay, so it says here, see again, says here again that let A be the k by n size matrix. So we want to show that a matrix A exists, right? So the matrix A here is Aij equals to 1 if Hj equals to 1. And how this looks like visually is that this is k, this is n. Then it says that if Hj, right, if one of the n elements, if it hashes to slot I, then you put 1 over there. Okay, so how this looks like is that let me see. So just now, for example, right, H5 equals to 1, H7 equals to 3. Okay, in that case, I will say that 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so let me just make it slightly bigger. You define this matrix and you claim that this matrix A, okay, H51 means that it's this guy over here. This is 1. Okay, H73 is this guy over here. Okay, so you define this matrix. Define this matrix where the Aij entry is 1. So like the 3, 7 entry is 1 because the H7 equals to 3. Okay, then so far, like, do you understand the construction of this matrix? Sorry, okay, that's great. So now what we want to do, right, what the next line is arguing is that this table over here, right? So let me highlight this table over here. Okay, if we take this matrix A times our frequency vector at the end of the day, it's going to give us this frequency table. This table. Exactly. That is the argument that's trying to be brought about by this answer key. Yeah. So how does it do that? So observe that AFI, like let's focus on this. This is actually like we hope that it equals to T. We hope that the AF equals to T. Okay. So the I says that something like at the ith index of T, what is the result? Okay, so the result, right, by definition of matrix multiplication is the summation from J equals to 1 to N of this thing. Okay, let's try to visualize this. Okay, so AFI. So let's draw the same diagram again. This is K by N. This is N by 1 equals to K by 1, right? K by 1. So it says here that what is the, let's say this is the ith entry. What is the ith entry here? The ith entry here is by doing, let me try to recall what it's actually doing. FJ. Okay, wait, I forgot my matrix multiplications. Oh no, like which row times which row? I think it should be okay, it should be the ith row. Should be the ith row of ith row of this times the entire thing. Times the entire thing. I think. Right? So it says that let me multiply this row. Right? And notice how what's varying is that the J is varying from J equals to 1 to N. Right? That is exactly this. That's exactly this. So what you do is you take this guy times this guy, plus this guy times this guy, times plus this guy times this guy, plus this guy times this guy, and so on, right? So that will give you this entry. Okay, so this is what this thing is saying. Okay, so what this thing is saying. If it's too small, let me know, by the way. Like I just realized how it might not be as clear here. Okay, great. So the argument is that this value over here is actually equals to this. So now let's parse like what is this trying to say? Okay, so this is trying to say that what is it trying to say? So it's trying to say that if okay, let me process this. I understood this just now, but now I forgot. So this equals to, so remember this is 1 or 0, right? So this is 1, this is 1 or 0, right? So depending, so basically we kind of like ignore all the zeros because 0 times fj will be gone. Okay, so this is essentially just saying that it's the summation of j equals to of fj where aij equals to 1. Okay, which is equivalent to saying that where hj equals I by definition of this by how we constructed the matrix. Okay, so this is what this is saying. And what does that mean, right? It means that it corresponds exactly to the count slot in the IF slot. Why so? Because remember, in the algorithm, we are we are incrementing that slot whenever that slot is whenever we hash into that slot, you increment if we're gonna add. So, and whenever we delete, we decrement from that slot. Okay, so that also means that if we consider the final for every element, right? For every element that hashes to that slot, you just accumulate how many, what's the total sum to it. I think this part I didn't explain very well, but do you kind of like get the intuition, or do you want me to try and explain again? I think yes. Okay, yes, you got it. Okay. So yeah, so this is what this is saying. So the argument at the high level is saying that to show that it's a linear sketch, you find such a matrix A and you argue that the matrix A times the frequency vector is going to output the table that you are actually maintaining in the algorithm. So that's what the part A is trying to do. Okay. Do you need me to go through part B? Okay, you can read first. Okay, sure. So okay, sure. So I'll pause the recording first. If you want me to resume with part B, then just let me know. Okay, no problem. Okay, so as an extension to the previous question, there is a question: what does the notation, what the bracket n means? So if we go to the this notation, right? So what does square bracket n mean? So I forgot the exact one, but it's either it means like 1, 2 all the way to n, or it means or like because I don't know, I forgot which one, or it means 0 to n. I have a feeling that it's this one over here, because I think it's more intuitive saying that it's, if it's a square bracket n, it means like from 1 to n, meaning I have n elements, rather than following this definition. If I follow this definition, then there are n plus 1 elements. So I have a feeling that it's more likely that this is the definition used. So if anyone knows, like remember what Prof. Arnab said, you could chime in as well. I am more sure that this is the meaning. Okay, so I don't think this is the meaning of it. Okay. Yep. Okay, pause again. Okay, so there is this question being asked about this particular question from, I believe, the practice set for DP and greedy. So let me just put it down in the chat so that practice set DP question 4. Okay, so this is the question. So the question is asking, so let me just maybe go through it from top all the way, because I think so it says that I have an array of n positive integers with the total sum s and value k. Okay, then we just want to decide, we want to find if it exists, if it's possible to partition into k disjoint partition such that each partition contains s over k. So what does this mean? I don't know if I can come up with an example immediately, but the idea is that, let's say I have total sum of 15, right? Then I want to basically maybe make it 20. Let's make it total sum 20, and the value of k maybe like 4, right? So we want, let's say we have this input, right? So we want to partition it into 5 pieces. 4 pieces, to 4 pieces, 4 equal pieces, such that each of this is 5. Right? We don't know how, but basically the question wants you to decide, like, is it possible that this particular array, right? This particular array of sum of 20, can we divide it into exactly 4 parts? Okay, so that's what the S over K means. Okay, so okay, so the idea, the intuition that they try to say is that we try to fill each partition at a time. Okay, so we'll try to see if we can, like, look at each element and we try try to fill each partition, and we try our best so that we don't exceed to the next, we don't exceed our capacity. Like we must ensure that at all times, if we are adding it to a partition, we must ensure that the size is at most 5. Okay, so that's what this is trying to say, right? So if the unfilled partition overflows, we'll say that the set of values is impossible. So if like in any way, like if it's impossible, right, it means that one of it must have overflowed, right? Because if it doesn't overflow, if everything fits nicely, then we could divide. We can divide. Okay, so we'll store this value of unfilled partition in an array DP set, and we continue. Okay, so the idea that they try to propose is to maintain a bit mask to indicate which elements from S are used in the partitions and which are not. Okay, what does this mean? So this means, okay, 5332. So let's look at that. 5322, sorry. Then it says that this is the mid mask is 0110. Okay, so the notation they are saying is that if the mask is 0110, which is this guy, you are using 3 and 2 in the partition. So that means that you are using these elements currently in the partition. Okay, because this is what corresponds to the ones. Okay, then it says that the array will maintain an array DP and target. So take note, what does this target mean? The target here is S over K. Okay, so target is S over K. In our example here, this is 5. 5 in our example. So this is our target, right? Our partition must, sorry, it's very small, but the target is the S over K. So maybe I'll annotate it somewhere. Node cannot exceed target. Cannot exceed target. Okay, so in our example, that's 5. So the array DP will give the output for each mask as the sum of all values in the mask modulo target. Okay, so basically it's trying to say that, okay, let's say we use these elements, right? Let's say we use these 2 elements. If we use these 2 elements in our partition, right, we don't know whether we should take everything or we should only take 1 thing or 2 things or 3 things or n things, whether we should include everything in the partition. But what it's saying is that, let's say we take these 2 elements, right? So what's the sum? Let's see, array will give the output. Sum of all values in the mask modulo the target. Yeah, I mean, let me think slowly. Why did they suddenly put target equals 0? Okay, so I think what they are just saying is that the value in the DP table tells you the partitioning. Wait, sorry, I'm incoherent. So it tells you the total sum. If for example you use the numbers 3 and 2 in our partition, what is the value that we are using? Sorry. I'm very incoherent. So again, I'll repeat that again. So let's say I use the number 3 and 2. The DP of 0110 is telling me that the value of partition is 3 plus 2, and the 3 plus 2 comes from here. Okay, then the goal here is that we want it such that if we modulo the target, it equals to 0. I believe this is what it's trying to say. So the reason why we want this, the reason why this is nice, is because if for example, like, okay, this is actually a nice number, right? So we have 5. Let's say I choose the number 3 and the number 2 for this partition. So if I sum it up, I have 5, and I modulo the target. This is target. 5 modulo 5 equals 0. If it equals 0, it means that we just nice hit our target. We just nice hit S over K. Okay, so is this part confusing so far? But I thought each mask doesn't necessarily represent one partition. Okay, yes. So you are right in the sense that we want to ensure that DP111 will eventually be equals to 0. And this means, let me think. Let me think how to answer this. We'll give the output for each mask as the sum of all values in the mask modulo target. Okay, I think what this is saying is that DP of this thing is what happens if you choose. What happens if you choose? What happens if you choose this as a partition? Like maybe this could be like a combination of two partition and so on. Okay, so maybe like if for example like this could okay let me see. Let me read your answer again. Okay, you are right. This doesn't necessarily represent one partition. Yes, so my bad. So this could actually represent two partitions, right? So but I think the intuition that we can start off with is that it can represent either like a partition or the sum of partitions. If it represents like, for example, it represents two partitions, right? Then we want to ensure that all the sums we can divide exactly by 5. So you are right in the sense that this doesn't necessarily represent one partition. My bad over there. But I think as a starting point, like I like to think of it like maybe it's one partition first, but it can, as you mentioned, it can represent the sum of two partitions. But the goal here is that if we sum up all the partitions, it should be modulo 5, modulo the target, it should equals to 0. Okay, and indeed our target, we want to ensure that we can build DP1110, because what does this mean? Because we are already using all the elements, 11111 represents that we are using all the elements, and because we use all the elements, and somehow it just nice modulo each one of them, then it just nice it modulo target equals 0. That means that we can divide it into partitions as per needed. Okay, I think that explanation, the verbal explanation wasn't very well done, but wanted to check. Okay, let me see the argument. Saying that it represents two partitions, then 7 plus 3. Okay, so so this is you're right. So you're saying that 7 plus 3 also give us modulo 5 equals 0. And you are saying that this cannot be partitioned into 2, right? Cannot be partitioned into 2, because we cannot get like this is 5 and this is 5. So you are very right. You're actually right. But this is actually what our checks is preventing. So we are doing this check over here to ensure that each mask is still legal. Like if at some point it represents only one partition, it must be at most the target. The one you are saying, right, 7 plus 3, and like the target is 5. If the target is 5, then we couldn't have created this partition. We couldn't have, because this 7 is too much. It will exceed the target already. So we couldn't have created that partition. So it will not actually like update. At least to my understanding. I think that's what's going on. At least the representation makes sense so far. I'll wait for a signal before going on. It's prevented. Okay, nice. So you get the idea. Prevented by the at most equals to check. Okay, so okay. So now we hopefully we get the rough idea of the representation. And I must say, like, I think this question sounds pretty difficult if you try to come up with the idea yourself. Just remember, partition is NP-complete. That's why like even with DP solution, you still get exponential runtime. Okay, so in this representation, we want to transition from mask by adding element J. It is achieved by bitwise or operation as follows. So Okay, so wow, this notation, they are missing a, I think they're missing a opening bracket. Okay, I think this is probably their notation for like square brackets. Okay, dpi okay, I think let's ignore this part first. I think the code was making more sense. So let's see first. We can check for the following conditions. If k equals to 1, make one partition for all elements in S. Then return true. Okay. If k greater than the size of S, then return false. So this is base case checks. Okay. So I think I won't talk too much about this part. Let's go through the main bulk of the code, which I think is the more interesting part. So these are just base cases or edge cases, however, base slash edge case, base slash edge cases. Okay, next we can update the DP array as follows. So what you do is that you first initialize it with -1. Okay. Then dp0 equals 0. This simply means that dp0 is 0, 0, 0, which just means like haven't taken anything. Haven't taken. Then the target is S over K, right? Target is S over K. We want to ensure that each partition never exceeds the target. Okay, so then we say for mask in range of 1n. So do you understand this syntax? Just wanted to check. Okay, great. So yeah, so this is iterating over all the subsets, over all 2 power n subsets from 000 to like 111, something like that. Okay, so if the current mask is invalid, then continue. Okay, so I think that's not as interesting as the next one. So what it does is that now it want to check, right? Let's say I have the current mask. I have the current mask of maybe for example 0, 0, 1, 0 for something like that. Okay. Then for I in range of n, what it's doing is iterating through this element, this element, this element, this element, this element, or maybe in the reverse order. Okay, but it iterates through all these things. Then this check over here, right, is trying to say, let me check the current mask. Have I chosen that element? Because remember, what this is doing, right, is that want to add index, want to add element at index I. So you want to see whether whether the bit mask is 0 at the position, at the index, right? So for example, if we are trying to add maybe index 2, right? Oh, sorry, I equals 0, 1, 2, 3, 4. If we want to try adding at the index 1, then it's 0 at that bit mask. It's saying that I haven't taken, for this mask, I haven't taken this element. So I can choose to take it. Okay. But otherwise, if I do, if I check at the third index, if I'm trying to get the third index, actually the mask is telling me that I have taken the element at the third index. So I cannot take it. So this is what the first check is doing. Okay. If you want to try understand, this is like, this part over here is you start off with like 1, and then the right shift is basically doing like push, append zeros behind it, and then the end operation is checking the end between these two things. So you're just end of these things and ensuring that it is indeed 0. Roughly, that's what it's trying to do. Okay. Then the next thing you do is that you check. So now if you pass the first check, if you pass check 1, it means you can take the item. Okay. If you do this check 2, it means that by taking that item, so remember, DP mask tells you what's your current capacity, like, sorry, how many elements, how much do you sum up to at this point? Okay, how much do you sum up to at this point? And then you try to add the element at that index. Okay, try to add the element at the index. You must ensure that you don't exceed the partition limit. Okay, you must ensure that you never exceed the partition limit, because otherwise, as you proposed earlier, it will come into this kind of situation if we allow that. Okay, so we try to ensure that it doesn't violate our partition limit. Okay, then what does this transition do? So this transition, oh, I see. So this is a bitwise OR. This is a bitwise OR. So it's trying to say is that very simple. Let's say initial mask is 00010. Then trying to add element at index 1, for example. By the way, I might have like gone the opposite direction for the indexing, but I hope just to get idea first. It's trying to say the one. Okay, sorry. Let me restart the mask. Let's say the mask is like 10010. Okay, so the one right shift, left shift by I is maybe like something like this maybe. So this is, let's say this is the one left shift by I. Then you do a modulus bitwise OR to get 11010. Okay, so because this is 1, then this is 1, this is 0, this is 1, and this is 0. So this is what the transition is doing. It's trying to update. It's trying to update the next part. It's trying to update the next part and ensuring that you're adding to that index. The bit masking is doing the right thing. The bit masking is trying to put to signify that you are taking the element at that index. Okay, so this is the bit mask, and then the DP mask plus this is simply like, well, it's basically this check over here and ensuring it's modulo the target. So modulo the target allows us to like make it equals to 0 for the if in case like it just nice hits the target. So this is the case of like just nice hit target. Okay, so did I lose you? This is the part you were gonna ask, right? The transition. Every mask represent one partition. Let me think. Let me think how I can explain this best. So maybe the first time, right? Like you can think of it as the first time. Let me think. So the short answer is that it doesn't represent a single partition actually, but it can represent multiple partition, given that I think the other partition is exactly the target. So that's a confusing statement. Let me try to think of a like exact example to like maybe convince you what I'm trying to say. Okay, so maybe let's see, maybe the elements is 2, 3, 4, 1. Okay, so the bit masks. So remember this 0, 1, 2, 3. Bit mask and the DP value, right? So the bit mask 1000, DP is 2, right? Okay, let's say we are trying to divide it into k equals to 2, right? So we want to see whether the target 5 is feasible. Target is 10 divided by 2, which is 5. 10 comes from the summation. Okay, so bit mask of 1000 represents the DP mask is equals to 2, right? 1001, for example, is representing 3. Okay, then 1100, 3 because this is equals to 2 plus 1. Okay, I hope you follow. It's from these two. 1100 is 2 plus 3 modulo 5, because 2 is this guy, 3 is this guy, modulo 5 is because you want to modulo the target. This is equals 0. This is equals 0, right? Okay. The bit mask 1101 represents 1. And this comes from this comes from 2 plus 3 plus 1 modulo 5 equals 1. So this particular bit mask over here, it kind of like represents, it kind of in a sense, right? It represents two partitions, like this guy and this guy, in a sense, but let me think how to best explain this, because what I'm saying is like it kind of represents two partitions is because it was derived from maybe this guy. This guy is like a whole partition that has been fulfilled. Okay, so your question says, does it fill one partition at a time so it doesn't fill other partitions if the current one isn't filled up? In a sense, yeah. So it fills one partition at a time so that it doesn't fill the other partitions if the current one isn't filled up yet. Yes. So I guess you can think of it that way. I think that was the intuition that they're trying to give. We try to fill each partition at a time, then we try to add it into the unfilled partition. Okay, so I've got a private chat question. Why is 1000 okay, why is the DP mask 2? So remember, the bit mask is telling you what elements you are taking. Okay, the bit mask 100 means that this is, I'm taking 2, but I don't take anything else. So this is what the bit mask 1000 means. Yes, from the original array. Yes, no problem. Okay, so yeah, so like the remark I received earlier on, I think is correct. It's saying that we are trying to fill one partition at a time so it doesn't fill up the other partition if the current one isn't filled up. Because you're trying to fill up this one over here and see, nice, 2 plus 3 modulo 5 is 0. So I filled up one partition. Then I try to bit mask this one over here. Ordering, like ignore my ordering, but it's just to illustrate the point that if I do 1101, it comes from 1100 plus this guy over here, which is 1. If, for example, I do another example, 1110, well, it comes from like maybe this guy, like the 0 over here, plus 4, right? Because the original array has 4. So it's saying that the value if I add it up is equals to 4. Modulo 5 equals 4. Or you can think of it as like 2 plus 3 plus 4 modulo 5. That's fine also. Equals 4. Okay. Then so is this clearer? Yep, nice. So just maybe to conclude the discussion, is trying to now access, right? This syntax over here is just trying to get the mask 11111 n times, right? Y minus 1, I leave it to think of you why. Okay, this is bit manipulation, but this is essentially trying to access 11111 to see if it equals to 0. See if equals 0 means that we fill up everything nicely. We fill up each partition very, very nicely. If it's possible that we reach DP 111 equals 0, it means that we fill up the partition very nicely. Fill up very nicely, following our constraint that each partition must never exceed the limit of the partitioning. The target must not exceed the target. If we manage to reach this, it means that every partition we fill up follows this constraint. And at the same time, because it follows this constraint, then it's very nicely like, that means like it's exactly equals to the target. Okay, I think that wasn't exactly well phrased, but the point is that this check here is to ensure that everything fills up nicely to be equals to the target. Okay, because otherwise that means one of the partition must be like overflowing or something, or it's not sufficient to use everything and we don't get exact. What a difficult question to explain. Yes, so do we populate the DP table in the mask order of 000? So the question is like, what's the order of populating the DP table? Yes, so I believe the order is done as you said, 0, 0, 0 to 1, 1, 1 because of this over here. So this is essentially saying populate it in this order. And let me think whether there's a valid ordering, right? Like seems it's interesting whether or not it's a valid ordering or not. It's so huge. The ordering a bit sus. Yeah, I feel you. Let me think. So if I start from 0, 0, 0, what happens, right? So I start from 0, 0, 0. The inner loop will check the 0, 0, 0, 1, will check the 0, 0. Okay, so this is starting point. The inner loop will do all these things. Do all these things. Okay, so it'll do all these things. And if it's legal, then you add it in. So then once you have one element, I have a feeling this is the, oh, let me think. This DP mask, right? -1. Okay, let me think. I have a feeling because of this final bit being set, it might represent like a +1, you know, like checking the ensuring that you have already checked all of it. What I mean, give me a moment. So if for example I have the number 00110, have I okay. Okay. I see 1110. Okay. I think I can give an intuition of the argument why like the ordering is fine. Okay. So you consider any mask, right? Consider any mask. Okay, maybe we consider any mask. Like let's say for example, like for the sake of argument, 10110, right? We want to ensure, like, to convince ourselves that ordering is fine, we want to ensure that this value is already like up to date, right? Like we want to say that like we have correctly updated our DP table to know whether or not like this what the value of this is. This is the argument we are trying to bring about. Okay, and why is this legal, right? So basically you want to ensure that for this particular example, we want to ensure that we have checked 00110, we have checked 10010. Basically, like all the ones I assume like I've removed. Assume I've removed something like this. Assume I've removed like the ones individually. I want to check that. I have considered, assuming this is correct. So wishful thinking a bit. Assuming this is correct, then I add the 1 in this position, right? So the reason the ordering is, I think, fine is because if you think about this, if I remove a 1 and make it 0, okay, wait, first of all, do you understand like the argument I'm trying to say here? If it's confusing, I'll repeat. It's okay. If anyone listening also wants to chime in. Okay. So why I consider removing the ones individually is because this represents, right? Oops, my bad. This value represents that I am taking the element in the index, this index, and this index. I want to ensure that this value is the DP of this value. The DP of this value is properly updated already, right? It's properly updated, and who updates this value? This value is updated by remember the transition function, right? The transition function over here, the transition is adding 1 in. So like, for example, we start off with this mask 1 0 0 1 0. The next transition is by slotting in 1 at that index. 1 0 1 0. It's like slotting 1 in at that index. So now I'm thinking backwards. Starting from this, I want to ensure that I must have come from this mask bitwise OR with this. Yes, so these are like the one step before, correct. So this represents, I'm taking 3 items, right? Now I consider all the possibilities of where I came from, of all the 2 items that they are before me, right? So okay, let's say item 0 1 2 3 4. So this is basically the set. The partitions is considering items 0 2 and 3. So I want to consider all the possible step before, which is the item in set 2 3, item in set 0 3 and 0 2, right? So I want to ensure that this could only have been updated by these 3 possibilities. And I want to ensure that I have exactly visited these 3 things. Okay? So I have visited these 3 things, and these 3 things are making the update forward to this guy. I want to ensure that, is it really true? Like, to convince ourselves whether the ordering is fine, is to ensure that these 3 things must have updated this guy. And the reason these 3 things must have updated this guy is because if you like, I think intuitively, if you take away the ones and make it 0, all these 3 things must be smaller than this, right? So let's call this A, B, C, and let's call this D. So it must mean the raw value is A is less than D, and B less than D, and C less than D. So with this argument, it means that we must have visited these 3 values, A, B, and C, because of our ordering. We ordering starting from the smallest mask all the way up to the highest mask. So whenever we visit a particular mask, the ones that can update this mask must have been visited first, because they are bit masks that they are smaller than the bit mask we are at. Okay, I think that was like a quite an abstract argument, but yeah, it's good that you understand. That's great. Okay, so I think that also concludes. Hopefully, that concludes somewhat the discussion, like that the ordering is valid, and like the transition makes sense, and how do we why the answer we want to check this particular value. I think this is a difficult question. I had a hard time explaining, as you might have too. Yeah, it's quite cancerous to go through. Yes. Okay. So it's now 6 p.m. I can take maybe like 1 or 2 more questions if someone along the way had something. Okay. So I'll just wait here and wait until people leave, and after that I will just close the session. Thanks for coming. The next consultation, I'm planning to put at least 1 more. Most likely is next week Saturday, because I have exam next week on Wednesday and Saturday. So most likely after my Saturday exam, I will conduct it. Not tomorrow, but 1 week from now, either Saturday or Sunday. I also have exam on the same day as 3230, so I can't give a consult too close to the exam date either. Okay, I'll pause the recording. Then I think to conclude, yep, thanks a lot for watching.